I'd like to introduce Stephen Fromm from Michigan State University, who did his practicum at Los Alamos National Lab.
All right, so good afternoon, everybody. It's great seeing everybody here again in person. My name's Steve Fromm. I'm a grad student at Michigan State University. And today I'd like to talk to you a little bit about my research I've been doing in modeling general relativistic neutrino radiation transport, particularly in the context of neutron star mergers. So I'll start at the end of this and work backwards a little bit and start with neutron star mergers. Neutron stars are the remnant objects that massive stars can possibly leave behind when they end their lifetimes and collapse. If we have a binary system of these neutron stars over the course of 10 to the 6, 10 to the 7 years, they will in-spiral towards each other and violently collide, ejecting a significant amount of neutron-rich material that's at very high temperatures, high densities. Some of the intermediate objects that can be left behind as remnant objects from these mergers, like hypermassive neutron stars, are also very intense sources of neutrino radiation. And these neutron star mergers provide a set of conditions that are ideal for producing some of the heaviest elements that we know of in the universe, things like gold and platinum, uranium. You've heard about this a few times already this week. And this happens via a process called the rapid neutron capture process, or the R process, where when the neutron capture rates exceed the beta decay rates, I can't see that laser pointer very well, but we can build up these very neutron-rich heavy elements before they decay back down to something more stable. And the neutron star mergers provide an ideal site for this to occur, possibly one of the dominant ones in the universe. A few years ago in 2017, we did see observational evidence for the first time from multiple sources of a neutron star merger that did confirm some of this. So initially we saw a gravitational wave detection shown here on the bottom right from the LIGO and Virgo observatories, as well as some immediate follow-ups of the detection of a gamma ray burst. Using this information, we were able to triangulate where in the sky this came from, and we were able to pick up the electromagnetic signature when we pointed a bunch of telescopes at it, called a kilonova. It's kind of hard to see, but on the top inset, where's it? Oh, there's the pointer. In the top inset, there's a little black dot indicating where this transient actually was observed at. Digging in that particular signature a little bit more, over the course of the next 30 days or so, a number of different telescopes that were observing this object and in the multiple different observing bands picked up the magnitude of the light curve that it was producing. This, coupled with the data from the gravitational waves, we were able to make inferences about the properties of this merger, particularly about the mass that was ejected, how the temperature it was, the velocities it's moving, its composition. And this is what was able to indicate to us that the R process was indeed occurring in these sites. Now, to be able to understand what these observations mean and extract that data, we have to be able to model the neutron star mergers and the physics that are involved in them. This is a pretty complicated problem that truly pushes the definition of what multi-scale and multi-physics problems are. On the side of the observations, we're dealing with things that are potentially tens or hundreds of megaparsecs away, that we're making observations on the order of seconds up to about a month. On the opposite end, when we're trying to learn about the microphysics, in particular things like the nuclear reactions that are occurring, we have interactions that are occurring on possibly sub-femtometer levels and timescales that are approaching nanoseconds and shorter. Sitting here in the middle, the piece that will tie all this together and allow us to make some interpretations of the observations are our models and simulations. And even at this point, we are dealing with very disparate length and timescales that make modeling these problems complex computationally. Digging into one piece of these simulations and models that I'm most interested in and have done some work with is looking at the aftermath of the mergers, particularly the ejected material and the remnant objects, most notably hypermassive neutron stars, and looking in particular at how the composition of this ejected material evolves. The panels here on the left are showing a few time slices from a simulation a couple of years ago that we did that is showing how neutron-rich the material in this ejected matter is, as categorized or as quantified by the electron fraction YE. A lower electron fraction indicates more neutron-rich material. Immediately before the merger in the top left panel, we see that it's almost exclusively neutron-rich material, and its various forms of matter are ejected as time progresses. There are regions that are still incredibly neutron-rich. And this is where the simulations can get complicated and where neutrinos begin to play an important role. The matter that's ejected is still very dense, very hot, and the neutrinos that are being radiated by the remnant objects, these hypermassive neutron stars, are able to interact quite significantly with the matter in the ejecta. Depending on how we include these neutrinos in our simulations, we can get vastly different results in how the composition of the material evolves, and from that we can make predictions on nucleosynthesis of these heavier R process elements that can occur. To give a sample here, again from the same set of simulations in that paper a couple of years ago, we used two very approximate methods in neutrino of including the neutrinos in our simulations. And we see that when we're looking at the fractions of mass that are at various degrees of neutron richness here on the left, the different methods can give very different results. The projections that these have for the nucleosynthesis that we can extract from these simulations, while there's some agreement at some heavier elements produced by the R process, once we start getting down towards things around mass number 100, we do start seeing orders of magnitude difference that are predicted between these very approximate methods. So this here is a motivating factor for me to be able to try and model these neutrinos as accurately as possible. This can be complicated because to fully understand the evolution of the neutrinos, we have to be able to evolve their distribution function. For neutron-star mergers, these are highly dynamical events with a highly dynamic evolving space-time that we can only treat in full general relativity. And there's very high velocities that are also involved in this that are approaching the speed of light in some contexts. In full GR, evolving the distribution function is essentially evolving a 7-dimensional Boltzmann equation for every species of neutrino. That's not a very tractable problem to work with computationally. Glossing over a lot of the math that's here on the slide, we can do some degrees, or we can reduce the degrees of freedom by doing things like angular moment expansions, and eventually we can come up with a system of equations that I'm showing here on the bottom that shares some similarities to hydrodynamic equations. They're system of hyperbolic PDEs in conservative form, so we can apply a lot of methods that work in hydrodynamics to evolving the neutrinos. In particular, here we're evolving the neutrino energy density E and the momentum density F. We close the system in terms of the pressure. This is why it's referred to as an M1 closure. In a similar way, you would use an equation of state to close, provide the pressure for the fluid in terms of, say, the density and the internal energy. One thing to note here that makes this far more challenging to solve than the hydrodynamics problem is this middle term here in red, this energy flux term. We were not able to fully reduce the degrees of freedom in the moment expansion, and we're still left with what's essentially a fourth dimension to the problem. And this is the energies in the neutrinos. And these become important when we're looking at the interactions that the neutrinos have with the matter in the ejected material in these neutron-star mergers. And additionally, these interaction source terms here on the far right, the ones in gold, are where a bulk of the computational power is also going to have to go to solving these systems, because these are very stiff source terms in terms of the time integration. One thing more to note is that for every neutrino species and every energy of neutrinos that we are trying to look at, we get 4 equations. So this can very quickly outpace the computational memory costs of hydrodynamic solvers, as well as any solvers we might use for evolving the spacetime. Okay, so a little bit more on the math I was planning on talking about. I want to transition to talking about some of the work I've been doing over the past couple of years about building a general relativistic radiation transport solvers to model these neutrinos in the mergers. And recently, the code I've been working with, to give some background, is called FlashX. Flash and FlashX, it's a current iteration, been around for quite a while now. It's a composable multi-physics code, includes a number of different solvers. Part of what I've been involved in lately is developing general relativistic versions of some of these solvers in the framework necessary to couple these all together. Flash has been using adaptive mesh refinement via paramesh for a long time. More recently, it's included Amrex in addition to paramesh. It is mainly written in Fortran. This sometimes can present challenges in using some of these newer packages. Parallelization is, for the most part, has been pretty straightforward in MPI plus X parallelization scheme. More recent capabilities, we have been looking at adding GPU capabilities. Right now, this is mainly either through OpenMP Target and OpenACC, depending on which piece of the code we're looking at. A lot of this, I want to keep in mind, is still very much under active development. A lot of the testing is being done on the machines at Argonne and Oak Ridge. For practical purposes and day-to-day use, I use an Intel plus NVIDIA cluster that we have at Michigan State. There's been 2 main pieces that I've had to work in FlashX to be able to accomplish some of these prepping to do some of these neutron star merger simulations. And the first is restructuring how the time integration in FlashX has been handled. Previously, there was only a very simple operator split type time evolution where every physics unit took its own time step, kind of did its own thing, and before passing off control to the next physics solver. When you have a system of tightly coupled equations that are handled by multiple different solvers, makes it pretty difficult to produce a numerical scheme that is consistent with the underlying equations that we're solving. To work around this, I developed a new time integration scheme based on a method of lines discretization, which is very simply put, taking our system of PDEs and casting them as a system of ODEs that we can discretize in time, including just a number of different integration methods to work with this, some simple explicit Runge-Kutta methods, some implicit explicit methods for equations with stiff source terms. But the ones I've been mostly focused on are a set of multi-rate IMEX methods that take a implicit explicit scheme, but it can also incorporate a substepping in time at a faster scale that lets us handle these disparate timescales that do arise in these problems a little more smoothly. With all of that in place and some general infrastructure changes to accommodate this different integration scheme, as well as being able to handle some of the additional features we need for these general relativistic computations, I've been able to start building my general relativistic M1 neutrino transport code in FlashX. It's based on a version I previously have worked on in the Einstein toolkit. Like I mentioned earlier, it's very similar to the hydrodynamic equations, what we're solving. So a lot of these things are what you will typically find in some general relativistic hydrodynamic solvers. It's generally a finite volume scheme. We treat fluxes, geometric type source terms, and I also include the energy fluxes I mentioned before as part of the explicit time updates. What gets tricky, though, is with the different types and the different timescales involved in the neutrino matter interactions. Some of these have to be updated implicitly. Some of the other ones that kind of veer towards those shorter timescales, we can sometimes get away with doing multiple fast integration updates on the shorter timescale, doing the substepping that I mentioned before. One thing to note is because to do neutron star merger simulations, these all coupled together, all these different types of physics at different scales. There's also general relativistic versions of the hydrodynamics solver that are currently in development, as well as a space-time solver that are being worked on. These are not currently complete, so we cannot fully do a neutron star merger simulation or test these all coupled together. The one thing I'll show here real quickly, because I know time's starting to get a little short here, is this is exclusively a test prompt for the radiation transport for neutrinos that pushes the limits of the integration scheme by arbitrarily increasing the stiffness of the source terms for the interactions. Just to point out here on the right, this is a case that is an incredibly stiff source term that I have broken many of integration schemes with trying before, but it demonstrates that the multi-rate implicit explicit methods that I've built in FlashX are able to handle it pretty well. In this case, in the two plots that are here on the right. So, in summary, neutron star mergers are very extreme astrophysical events that serve as a pretty unique laboratory for observing some nuclear physics that we can't really replicate here, or under conditions we can't replicate here on Earth. Neutrinos play a very critical role during all this, but they also are one of the most challenging pieces to include in our models of these mergers. However, with all these exascale machines that are kind of on the horizon here coming online and a bunch of scientific codes that are being targeted and optimized towards these, we'll soon be in a position where we can run these very high resolution models that include all of these different physics at very different time scales and length scales, and hopefully achieve something more accurate than some of the very approximate methods that have been used already. So with that, I'd like to thank everybody here at CSGF and Krell for all the support that you've given me over the past 4 years. Especially would like to thank my former research advisor, Luke Roberts, for getting me kind of started on all this in the first place back even before the fellowship. And then, additionally, I'd like to thank my current research advisor, Sean Couch, and one of his students, Mike Pecos, for a lot of the work, a lot of assistance they've given me while I've been building all this stuff within FlashX. And with that, I'd be happy to take any questions that anybody has.